mix up a couple of these problems. I feel like there were some things that were hit really well last night, so I'm going to skip those and do them at the end. So rest assured, I will actually do all the problems, but I'm going to kind of do them in a different order just so that we have time to emphasize different stuff. So let's actually start on number 2. Number 2 is the only nomenclature we're going to do. I just want to hit E and Z stereochemistry one more time. I want to hit naming of alkenes one more time. Okay, so there is this new type of stereochemistry we need to learn called E and Z, and it's different than RNS. RNS is for chiral carbons, but looking at this double bond, for example, there's no chiral carbon there, but we may need to use E and Z stereochemistry to show that there is still stereochemistry even when there's not a chiral carbon. So what we're going to do, very first thing, we're going to slice all these double bonds in half. And then we're going to look at each side of them. We're just going to be comparing the left and the right sides. So let's get that. Cool. So let's look at the far left. On the left carbon here, we have 2 hydrogens, right? And then on the right, 1 hydrogen, and then a long carbon chain. We only need to do this stereochemistry if on both sides of our divider we have distinctly different groups. So let's look at our first double bond here. Let's look at the left side. Do we have distinctly different groups on that left side, or are those hydrogens exactly the same? The hydrogens are exactly the same, so we don't need to do E and Z here. We only need to do E and Z if we have distinct groups on both sides. So we can skip E and Z for this first one. No worries at all. Let's look at this second one in the middle here. Let's look at the left side. We'll call this A for now, and we'll call this B. Are A and B distinctly different? They're both carbon, but are they identical carbons? No, they're not, so they are different. Let's look at the right side. We have a hydrogen and a carbon chain. Different? Yes, so they're different on both sides. So for this middle double bond, we are going to need to show E and Z stereochemistry. Let's look at the last one. I'll do it kind of quick for you. We have 2 hydrogens on one side. Do we need to do E and Z? No. Yep, so it's only for when we have different groups on both sides. So now let's look at exactly how we go about this. We still have both sides divided. We're still just going to be looking at the left side only and the right side only at a time. What we're going to do now is we're going to decide between the 2 groups connected to the double bond, which one has higher priority. And we're going to do that based on atomic number. So we're going to look at these 2 groups here, call it A and B, to see which one is higher priority. They're both carbon, right? So we're going to have to break the tie. We're going to have to look and see what these things are connected to. So carbon A is connected to what? 3 hydrogens. Yep, H, H, H. Awesome. Carbon B, what do we have connected to it? A carbon, call that one, and another carbon, and there's a secret hydrogen there, hiding in line angle. So we have CCH. Now we compare those. We look at the very first one, H versus C. First point of difference, that breaks the tie. So which one of these, carbon A or carbon B, has higher priority? Carbon B. Yep, we're going to go down. Erase some of this. So carbon B. I'm going to label that real big. Now, let's look at the other side. We have a hydrogen and then some carbons. Which one has higher priority? The carbon. Yep, carbon's going to win. So that is the one we need to take care of. So now, we're going to get rid of this middle divider line. The one we did at the very beginning where we were slicing this way. We're going to get rid of that. Now we're looking along the length of the double bond. This is very similar to cis and trans. And remember, a cis double bond looks like this. That's a cis double bond. And this is a trans double bond. On the cis, see looking right down the middle, your groups are on the same side, cis. Trans, looking down the middle, your groups are on opposite sides. With E and Z stereochemistry, you're going to be looking at your high priority groups to see if they're cis or trans to each other. So if, like Sabrina said last night, if they're on the same side, is it going to be E or Z? Z. So cis and Z are associated with each other, and trans is E. Sorry about that, E. So now we're going to look back. high priority groups on the same side or different sides? Same side, so E or Z. Awesome, so there's Z stereochemistry at that double bond. Anyone have any questions about that? Raise your hand. We have some people coming around to answer questions. So if you don't know why we just picked that one double bond or how we got to Z, definitely get that question answered. Awesome, so we know that that has Z stereochemistry. And that's the only one we need to worry about. Now, let's actually start naming this thing, now that we've taken care of stereochemistry. What's the very first thing we do in a nomenclature problem? Longest carbon chain. Now there is a stipulation. We also need to find the longest carbon chain containing our parent functional group. That's very important because now we see that we have functional groups here, like our double bond, that are different from just an alkane. So now the definition is a little further than just longest carbon chain. We need to find the one with our parent functional group in it. So let's start just from the left. 1, 2, 3, 4, 5, 6, 7, 8. We could do that, or we could go from 4, 5, 6, 7. Which one wins? Go up. Yeah, you want 8. We're going to get rid of that. How do you know, though? So we're going from left and then up. How do we know to do that versus this? 1, 2, 3, 4, 5, etc., 6, 7, 8. How do we know? What do we do? We would look at what things are connected to, but what you're going to see is that all of these are completely identical to each other. So you could try to go out and break the tie infinitely and never get there. Those two groups on either side here are exactly the same. So one of them is going to have to be a part of the parent chain, one of them is going to have to be a substituent, but you're just going to pick because they're both completely identical and it's not going to make a difference. So we found our chain. 5, 6, 7, 8. Perfect. Now we need to figure out the order. We're going to try to put our substituents on the lowest numbers possible. So going from left to right, we have a double bond, ene on 1 and on 5. Going from right to left, we have 1, let's redraw this actually. 1, 2, 3, 4, 5, 6, 7, 8. So yeah, going from left to right like that, we have 1 on 3 and 1 on 7. Which one's going to win? 1 and 5, yeah, much lower numbers. So we're going to go from left to right. The eraser's huge. There we go. Awesome, so we have our parent chain and we've numbered it correctly. We have our stereochemistry done. Let's look at exactly what the parent is going to be for this. So before we ended things in ane because they were alkanes, do we have something that's higher priority now? Yes, alkenes. Those are going to take priority over alkanes. And so we're going to have to put that in the parent name because that's our new parent. So is it going to end in ane or ene? It's going to end in ene. Yeah, so if we have a carbon chain that is 8 carbons long, what's our prefix going to be? Oct. And then E. We might throw some numbers in there later. Let's just put that as our parent for now. We see we have, for substituents, we have our enes, like we said, on 1 and 5, but now we also have this complex substituent here that we need to name. How are we going to start numbering that substituent? Starting from the parent carbon chain. That's where we're going to start from. So let's use different colors. Use purple for this. 1, 2, and 3. So I started numbering at the carbon connected to the parent, not including the parent itself. So I didn't mark that as 1. Don't include the parent. So 1, 2, and 3. And what carbon is that on the parent? Carbon 4. So the whole thing is on 4. So we're going to start like that. Open it up with 4, because this whole thing is on 4. Now, how many carbons is it? 3. So what prefix are we going to use? Numeric prefix. Prop. Yep, prop. For prop. And how are we going to end this? We have ene, and then whenever we have substituents, we end in YL, so it's going to be propenol. YL. We also need to say where this double bond is. It could be here or here. We need to tell them which one it is. We know which one it is. So we're going to say it starts at 2 instead of starting at 1. Prop 2 enol. That's going to be our complex substituent name. You're also totally fine putting the 2 in front, 2-propenol. Those are both completely identical, both full points. All right, that's everything. We have both of our double bonds and the double bond in the complex substituent, but we also have our complex substituent. So we are ready to go. This here, the first one, ene 1 and 5, do we need to alphabetize that? No, it's automatically going to go at the end because it's a part of the parent. So we don't need to worry about alphabetizing that. This is the only substituent really that we're going to have. So we're going to start there. 4, prop, 2, enol.
We also have a method.
Methyl? Oh, I didn't even see that. I'm so sorry, you guys. This CH3, right there. Way to start it out. This CH3 right there, we need to account for that. Thanks for catching that, guys. So, like we said, on carbon 5, we have a methyl. Good catch, guys, thanks. So now we do need to worry about alphabetization. Now we need to look between the P in prop and the M in methyl. Which one's gonna win? Methyl, yeah, M-N-O-P. It's pretty close, but methyl's going to win. So we're going to start there. 5-methyl. 4, prop. 2, enol. Oct. And we're going to say where those double bonds are in the name of the parent. Octene. So oct 1, 5, ene. Did I do that right? Oct 1, 5, ene. We need to say how many double bonds there are, right? Right. So, we need to add a letter here. We have oct, we need to change it to octa, because we added that numeric prefix. So octa, and where were they? 1, 5. Sorry, it's getting run out of space. I'm going to move this down. Octa, 1, 5. Diene. One thing other than this we need to put on there is our stereochemistry. We found out at the beginning that that was Z. If it's the only double bond that has E and Z stereochemistry, do we need to worry about putting a number with it? No, we can just say Z. Yep, that's all we need to do. Z. There we go, that's our name. Z, 5-methyl, 4-prop-2-penol, octa, 1, 5, diene. Super long. Sometimes these will run over your boxes because the names start to get long. Don't worry about that, she'll still grade it. If you have any questions on that before we move on, raise your hands, get an answer. We're going to skip for now. We're going to come back to these stereochem problems later. I just wanted to hit this first so that we have more time for some other stuff. All right, moving on to facts. Favorite part of the test. Okay, consider the reaction below. In the box, draw the transition state for the rate determining step. So how do we know what the rate determining step is? Seems kind of like a crazy thing to know. First thing would be to figure out what type of reaction this actually is. One of the giveaways is going to be a reactant on the arrow here. We have CH3OH. Is that a weak base, strong base? What do we have there? What is that? It's a weak base. So with bases, better bases are higher on the periodic table, going up, so the highest on the periodic table, those are going to be better bases, and then to the left are going to be better bases. So for like O minus is going to be a better base than F minus, for example. So we know oxygen is right near the top, so it's going to be a base. Notice though, it's in CH3OH form, not methoxide, O minus. If it has that negative charge, is it weak or strong? Strong. So that would tell us something. It's not, we have weak. one of the things, the strength, whether or not it's a base or a nucleophile, the strength will actually tell you what order the equation is. And what that means, you have SN2, E2, SN1, E1. These are the second order. And these are the first order. The strength is going to tell you which of these orders you're going to be in. So if it's very strong, is it going to be a second order or a first order? Second order. Yeah, so the strength of your nucleophile or base is going to really drive that reaction, because if it's really strong, it doesn't need to wait for the leaving group to leave, like in the ones, like E1, SN1, the leaving group leaves first on its own. But if it's strong, it doesn't need to wait. So that's one of the biggest things that's going to automatically narrow it down to a 50-50. That should really help. So we know it's a base, we know it's a weak base. So what kind of reaction is this going to be? I mean SN1. But since it's first order, what does that mean about our rate determining step? The very first step, when that leaving group leaves and forms a carbocation, that's our rate determining step. No matter what, for any of our first order reactions, that's going to be our rate determining step. So we know it's going to be this, the bond breaking, the electrons going to bromine, and the formation of this carbocation right here. But they want us to draw the transition state. They want us to show that happening. So what we're going to do, I'm going to draw a molecule. And we know that that bromine bond is breaking. So we're actually going to put that in a dashed line. BR. Okay, now we can look at this. So when the bromine has fully left, when it's already gone, what's its charge? Negative charge. While it's on the molecule, what's its charge? Neutral. So it's going from neutral to negative. So during this process, it's going to have a partial negative charge on it. How about the carbon it's attached to? What's its charge before anything happens, while the BR is still on? Neutral. What's its charge after? Positive. So it's going towards a positive charge. We're going to need to put a partial positive charge there. And there it is. That is the transition state for your rate determining step.
So this was E1?
This is going to be a combination of SN1 and E1. Usually they'll go together. So when you have a weak base like that, you'll have both substitution and elimination products. Good question though. Almost always they'll go as a pair. SN2 and E2 are much more distinct reactions. We can talk more about that when we get into bulkiness and stuff like that, but we'll definitely do that. If you have any questions on transition states, raise your hand and get that question answered. Okay, moving on. Place the following carbocations in order of increasing stability. This is just kind of a memorization question a little bit. For carbocations, what's the trend in stability? What do you want a carbocation to be, primary or tertiary? You actually want it to be primary. It's the opposite from your carbocation rule. So carbocations want tertiary substrates, I guess. They want to be on a tertiary carbon because they're stabilized by induction. So let's look here just for a second at this tertiary carbon. There's electron donation happening by induction from each of the carbons it's attached to. So it's getting some extra electron density. So say we put a full negative charge on that bad boy, and it's getting a lot of extra density. Is that good? No, the more groups it has on it, the more density it's going to get, the worse it's going to be, the more unstable it's going to be. So we actually want that thing to be primary. Closer to primary, the better. So looking at this, let's list off what these are. So the far left one is secondary, middle, secondary. So we're going to have to... The only difference here, so we look at this carbon on both of them. On the left, there are two hydrogens. On the right, there's a hydrogen and a chlorine. What's that chlorine going to do? Is it going to withdraw or is it going to donate density? So that chlorine is going to withdraw a little more density than would normally happen. So then this, if you're comparing this hydrogen and this chlorine, the chlorine's going to withdraw more. So there's going to be a little bit more withdrawal going this way, out of that anion. Is that going to reduce the amount of negative charge in there or increase the amount of negative charge? It's going to reduce it. Yeah, it's pulling some of these electrons away. Yeah. So if it reduces the amount of electron density in that negative charge, is that a good thing or a bad thing? Good thing. It's already too negative. It wants to be less negative. So this one is going to be more stable because chlorine is going to take some of that density out. It's going to be a little bit of a help, whereas this one over here has no help at all. If you have any questions on that, raise your hands. Get them answered for sure. I'm going to skip this one. Dr. Bean sent me an email. This is not on the exam. So you're set. Yeah, this is not on the exam. I think she said something about anything in a certain quiz being fair game, but she just emailed me. She said she's not going to cover it. We're set to go. She said to not even do the problem. So, and there's another one in here that we're not even going to do. So we're skipping that one. Hooray. Congrats. All right. So, label each of the compounds below as chiral or achiral. So this is actually going to be a different story than just our carbons, because there may be chiral carbons in a compound that's achiral. We're going to look at why. So looking at this left compound first, are there any chiral carbons in this thing? Yes, yeah, so this top one right here is chiral. Bottom one right here is chiral. The middle one, is the middle one chiral? No, yeah. Both of these are actually exactly the same. So that middle group is not chiral. It doesn't have all four distinct groups. So we have two chiral carbons here. Is there anything else we look for when we're talking about chirality of molecules? Planes of symmetry, that's going to be the big giveaway here. So looking at this molecule, is there any place we can draw a plane of symmetry? If we draw a plane right through the middle here, you're allowed to cut atoms in half. That's still a plane of symmetry. We notice on both sides, everything is exactly the same. Total perfect mirror image, internal plane of symmetry. What that means is that both of these chiral centers will reverse the effects of each other. So overall, the net molecule is going to be achiral because there's that internal plane of symmetry. These two chiral carbons will reverse the effects of the other. So it'll be completely neutral. So this is an achiral compound, even though it has chiral carbons. Raise your hand if you don't get that distinction. Achiral. Okay, this one. This is kind of brutal, honestly. I think this picture is a little bit misleading. So first thing I want to point out, look at these two carbons. How are they hybridized? They're hybridized sp2. How are the bonds organized in sp2? Are they planar? They are planar. Yeah, they're planar. So this, right here, these three bonds are all supposed to be in the same plane. So why is there a wedge there? It seems really strange, right? What she's trying to show here is that this ring right here, the one on the left, is flat. One of the eyes is in the back, one of the eyes is in the front. And then it's connected to a ring that is perpendicular to it. Bromine up, eye down. So it's not that on the left here, it's not that one of the eyes is pointing down from the benzene ring and one of the eyes is pointing up. It's a little misleading. It's all in one plane. So I'll do this backwards. Here's your left one, and you have your iodines on both sides. Here's the right one, totally perpendicular. You have your Br on top and the I on the bottom. I's on both sides here. Is there a plane of symmetry here? Yeah. If you look from bird's eye view, from up top, you can cut this thing straight down the middle. So the bromine's up top, I's the bottom, you can cut those atoms in half. The whole phenyl ring over here gets cut in half. And then on the right, you slice it down the middle, one eye on each side. So there is a plane of symmetry here, and so this thing is actually achiral. It's tricky. I have one question for you. I highly doubt this is going to show up on the exam. The only way it might show up on the exam, I think, would be this. If she changed out this I for a CL or something similar. How about now? Now what's your answer? It's chiral. Yeah, because before on this one we had I's on both sides, so we can cut it straight down the middle like that. If you change it to where you have a CL and an I, you're going to have a different thing on both sides of your plane of symmetry, which isn't now really a plane of symmetry anymore. That's about the only way I think that would come up. I doubt she would completely repeat a problem. Yeah, what's up? It's all right. So I was just asked if the double bonds matter. And it's actually those double bonds precisely that are making this whole system, these three bonds here, it's those double bonds that are making it planar. This thing is sp2 hybridized. And that means those three hybrid orbitals here, making the three sigma bonds, they're all in the same plane. So it's just kind of a frustrating question. We can talk about it more afterwards. Those are about what I just showed are really the only two examples of this problem you could possibly see. So if you see it, you're going to know how to do it. So that's good. That was the goal. All right. Let's go on to number 5. In the box provided, place the letter of the reaction with the faster rate. Faster rate. If the rate is the same, write S for same in the box. Let's figure out what kind of reaction we got here. Let's look at our substrate first here. What do we have? Bromomethane. So are there any carbons but that one carbon? No. Can we have any elimination reactions here? No. Yeah, we can't have any elimination reactions because those elimination reactions form a carbon-carbon double bond, right? So if we only have one carbon, can we proceed by the elimination pathway? Nope. Yeah, so we automatically rule out both of our eliminations. So this is either going to be SN1 or SN2. Now we look. The only difference here, we have sulfur versus phosphorus. And then also the number of these carbon chains coming off because of how each of those bond. With nucleophilicity, so these are going to behave as nucleophiles now, because remember we eliminated our elimination pathway, but now it's just substitutions that we have. So is it going to act as a base or a nucleophile? Be a nucleophile. Both of the substitutions, they act as nucleophiles. So now we're looking at nucleophilic trends. So trends for nucleophiles, this is different from bases. This is really the big piece that's different from bases. They get stronger as you go down the periodic table. What happens as you go down is that the orbitals get significantly bigger. So like the 4s orbital is way bigger than the 2s orbital. And as you go down the periodic table, you're going to get into those bigger orbitals. What that means is that electron density is more easily polarizable. It can go make a nucleophilic attack much easier than something's really tightly bound, like oxygen or something is really tightly bound. Sulfur's going to have a lot more room. So going down, you get stronger. This is the same as bases. Going left, you get stronger. So this same as bases, this is different. So that might help you. If you're trying to decide between sulfur and oxygen or something, which one's the nucleophile? Sulfur, for sure. So I'm going to erase that just so I can test it all. Looking at this, sulfur versus phosphorus. You are provided a periodic table. Which one is further to the left on the periodic table? Phosphorus. So is phosphorus going to be stronger than sulfur? Yes. So phosphorus is going to be our stronger nucleophile. We decided that it was an elimination. How are we going to decide now between SN2 and SN1? I would look at the substrate for this problem. CH3Br. If it were SN1, the leaving group would have to leave right at the beginning, and that generates a carbocation. How stable is a methyl carbocation? Horrible. It wants to be tertiary. Tertiary is the best, but as you go down, it gets worse. And this is methyl, so that's as bad as it gets. You don't want that methyl carbocation. So is this going to proceed by SN1? No, yeah, it's not going to proceed by SN1. So we've eliminated everything, and now we just have SN2. So we know this is an SN2 reaction. We know the rate law for an SN2 depends both on the concentration of the nucleophile and on the concentration of the substrate. So if we have a stronger nucleophile in here, on B, if that nucleophile is stronger, is that going to increase our rate? Yes. Yes, it will. So the nucleophile matters in the second order reactions, SN2 and E2. The strength of the nucleophile or the base matters a lot. So the one with the stronger nucleophile is going to proceed faster or slower? Faster. Which one is that, A or B? B. If you have any questions on that, raise your hand. Definitely get questions answered. This is super tricky. Come to me after too if you're ever, confused about stuff, just want to work through problems. I'll be here till 11 o'clock. I don't really care. Okay. Here's a part where a lot of people lose a lot of points. So I'm going to show you a couple different techniques that might save you some points. So label each of the following pairs as identical structural isomers, conformational isomers, and antiomers or diastereomers. That's a big, long list. What are we talking about? These are isomers. So isomers have all of the same atoms, but they may be connected differently, like they may be connected to different carbons, the bonds might be in a different order, or they may be in a different orientation in space. All of these different words describe all of those different scenarios. We see here some Fisher projections too. With all Fisher projections, we're going to draw our bow ties. Everything on the side, both the left and the right sides, are going to be on wedges. Everything up and down, dashes. And you can do that on every single one of your Fisher projections. Makes them kind of look snazzy and stuff too, so might as well have some fun while you're suffering, Anyway. So, first technique I'm going to cover with you guys is the pinch and hold technique. So when you're trying to decide whether Fisher projections are identical or what have you, and you want to change the orientation of it so you can see it better, one thing you can do, pinch and hold. Up equatorial. Up axial. It's going to be up axial, that hydrogen. Let's go to the next up hydrogen. How about that? Up equatorial. Yeah. How about this up hydrogen? Up axial. Yeah, you keep going around the ring. Now it's not a hydrogen, it's up chlorine. How about that? Up equatorial. What did we say earlier? We need them to be transdiaxial. That's the axial piece. We need that leaving group to be axial. But we just showed, because this super bulky group is here, it's going to be forced in the equatorial position. Let's go ahead and draw that. Let's go around the ring. So we have one carbon here, 2 carbons over clockwise. We have our chlorine up. So we're going to go 2 carbons over clockwise, 1 carbon, 2 carbons. Chlorine is going to be up equatorial. Good or bad? Bad. Yeah, so what needs to happen in order for this E2 to happen? The chair conformation needs to change. It needs to change to the other conformation. Is that going to happen very often? Not really at all. It's almost predominantly going to exist in this conformation. So is E2 going to happen very rapidly? No. That's a tricky one, because on first glance, what you might think is that, oh, there are hydrogens next to that chlorine. It's fine, let's just do it. But you have to check that chair conformation. Make sure it's axial. I'm going to skip this one. This is also not on your exam. The reason for it, it generates a bridgehead double bond, and that was the concept that she said was not going to be on the exam. And that was the whole reason why this was a no. Just for the record, it is a no because you generate a double bond at a bridgehead carbon. That's the reason for it, but that is not on your exam, so we're not going to go through this. Moving on, reactions. This is the great part of this exam. Whatever you want to say is great, whatever that means. Okay, reactions. This is really tricky. There is a chunk in your book that you really, really should read if you get the chance. I know reading the book isn't necessarily the greatest experience, but it's page 271, and it finishes at 273. So it's just a couple pages. What this is a guide for predicting whether it's going to be SN2, E2, SN1, or E1. And it's a great guide. It's super helpful. Look at the very first bullet point. Sorry, this is page 271 in your book. I think 7th or 8th. It should be right close to the same page number if you have a different edition. I'm not sure which edition I have. It'll be right in that ballpark. Good question, but I don't know. The very first bullet point, strength of the base or nucleophile determines the order of the reaction. We talked about that earlier. If you have the order of the reaction determined, you've already narrowed it down to 50-50. So just understanding that very first bullet point of the list, you've already eliminated 50% of your choices. That's huge. That'll help you a ton. And there are more helpful things as you go along. So if you really master just those 2 pages of the book, you're really going to do well in the reaction section. So if you get the chance, especially tonight, tomorrow, as soon as you can, read that. It'll really help your studies a lot. Let's go ahead and dig in. So let's go back to that first bullet point that we actually just talked about. The strength determines the order. Is this strong or weak? It's weak. Yeah, its strong counterpart would be the ethoxide anion. O-. That's the strong counterpart to this molecule. We don't see that though. That's not what we're using. So it's weak. This is also going to act as a solvent. Let's talk about solvents for a second. Is this a protic or aprotic solvent? It's a protic solvent. The reason that matters is that protic solvents will increase ionization. That's a long form way of saying that it's going to encourage the ones. It's going to encourage SN1 and E1. That protic solvent is going to make the leaving group leaving much easier. And that's the rate determining step. So if you can ease up the rate determining step, great. That's going to help a lot. So this is a protic solvent, and it's going to encourage SN1, E1. Also, remember, it's weak. So again, we're encouraging one of the ones. So this is probably going to be a mix of SN1 and E1. Almost all the time, they will occur together, SN1 and E1, because they share that first common step. So oftentimes, that initiation step will lead to both reactions. Another thing we can look at, just to confirm our suspicion that this is going to be SN1 and E1, is our substrate. Oh no. Is my pen going away? Oh, we're good. Never mind. Our substrate. What is that bromine connected to? There's a tertiary carbon here. When that bromine leaves, we form a what? A carbocation. Is that more or less stable on a tertiary carbon? More. Yeah, it's stabilized in a tertiary carbon. So is that leaving group leaving going to happen pretty easily? It is, yeah. So pretty much everything here is pointing to SN1 and E1. So this is going to be SN1E1. You don't need to draw steps of the reaction or anything. I'm going to go ahead and draw them just so you can see them. Don't put them on your exam. Just draw the final product of whichever reagent you're using. Let's redraw it. Our bromine left, right? Sorry. Took the electrons with it, which is why we had that positive charge. We lost electrons. The bromine took them away. So we have that positive charge here. Now, we see here on the boxes we have major, minor, minor. We have 3 products. Ugh, we're only doing 2 reactions. Spooky. We'll figure it out. What we're going to do to determine major or minor is look at the bulkiness of our base or our nucleophile. If this were tert-butyl alcohol, it's weak, but it's huge, right? Is that going to go more E1 or SN1? It's going to tend towards elimination. Yeah, the bulkier ones are going to tend towards the E ones. So if this were super bulky, you would tend towards your elimination reactions. Is this super bulky though? Not really. I mean, a little bit. It's a little bulkier than the CH3OH like that, but it's still small enough that it can get into substitute. So SN1 is actually going to predominate in this case. So let's, for our SN1, let's draw this mechanism, CH3, CH2, OH. We have these electrons here. They go in and attack our electrophilic site. Our nucleophile will attack our electrophile. That's a common theme you're going to see forever and ever. The nucleophile will attack the electrophile. Uses those lone pairs to form a new bond. So let's draw what that would look like here. Something happened here to get rid of the hydrogen. I skipped a step. What was it? Deprotonation. That's very important. Yeah. So when this reaction happens, that first step that I just drew, what you're going to get is this. I'm going to erase this later for more space. But you get this where you have your O, CH2, CH3, and that's still connected to another hydrogen. What's the charge on that oxygen? Positive. Yeah, our charge is conserved. Yeah, because that positive charge in the carbocation just moved over to the oxygen. Positive charge there. So now we're going to need another CH3, CH2, OH to take that off. That's the only thing we're given to take that off. There's nothing else in there but heat, and heat isn't going to actually do anything for us as far as taking off a proton. So this CH3, CH2OH, ethyl alcohol, is going to go grab that hydrogen, form a new bond with the hydrogen. That's going to cause the OH bond here to break. And those electrons are going to go off onto the oxygen. If you weren't sure, what would help tell you that the electrons go to the oxygen? It's positively charged, right? This oxygen is positively charged. So electrons going towards that positive charge, that's a good thing. Also notice in our product, it's neutral. Where did the positive charge go? Remember, our charge is conserved. Where did it go? It went onto this guy. It went onto our base that came by and grabbed the proton. So it's still there. It's just not on our product. Charge really is always conserved. Okay, so that's our major substitution product there. Do we have any other products for substitution? We don't need to worry about stereochemistry in this case. Stereochemistry isn't given. And this carbon, oh no, sorry. This carbon isn't even chiral either. So we don't need to worry about stereochemistry here. The two other products are going to come from two different elimination reactions. Let's go ahead and draw those. Let me go ahead and erase this as well. That's right, isn't it? I'm not missing the carbons. Yeah, okay, cool. Okay, so we've got our positive charge. Notice the things attached to the carbocation, the things attached to our positive charge. We have a CH3, and a CH2. Notice. So one of them is a CH2. Are all of those eliminations the exact same? So if you take the proton from the CH2, the CH3, or the CH3, are they all the same? No, they're different. If you took one from the CH2, if you took a proton from the CH2, you would generate your double bond right here, where you took your proton from. Is that more or less substituted than our alternative? It's more substitutes. We have 3 substituents on that double bond. What I mean by substituents, you look at your double bond, and then you look at how many things are connected to it that aren't hydrogen. All you care is that they're not hydrogen. So we have 1 group here, 2 groups here, 3 groups here. This is tri-substituted. And that's going to be pretty stable compared to if we put our double bond here, which is the alternative. Is putting it up top here and down here, are those the same? Yep, they're both CH3s, totally identical. You can pick whichever one you want. No big deal. So now let's look at how many substitutions this thing has. Let's change colors again. On our double bond here, we have 1, 2. That's dye substituted. So if we can, we're going to try to go for that tri-substituted product. That's the whole thing, if we can. In this case, we can because our base isn't very bulky. It's small enough that it can get in here and abstract a proton from the secondary carbon. It doesn't need to resort to this carbon way out here because it's too bulky or something. It just goes straight for the best one because it's small enough, it isn't sterically hindered enough that causes that to be an impossibility. So our major product is going to be the more stable double bond out of the two. Looks like though she actually doesn't care between each of these which one's the major or minor. So you can actually just put them. Doesn't even matter. If you were asked to rate them, that's how you would do it. If you were asked to rate which minor product was less minor or something like that, that's how you would go about it. But in this case, we can just draw both possibilities. Because it looks like she don't care. So there's our tri-substituted double bond, and here's our di-substituted double bond. Yes, so in this case, SN1 is more major because it's small. Our reagent is small. Base or nucleophile, it can act as either. But it's small enough. So if it were super bulky, would it want to substitute? Could it really do substitutions very easily? Not really, not typically, especially on like tertiary sites. So in this case, it's a tertiary site. Tert butyl alcohol is never getting into a tertiary site. That's just not gonna happen. So eliminations would be favored if it were tert butyl alcohol. In this case, it's not, it's small, so our substitutions are favored. Yeah, what's up? The say again? Anti-elimination. Oh, like sin eliminations and anti-eliminations? They're all anti-eliminations. So Dr. Bean actually doesn't really even teach sin elimination. So that's not even that. They're all going to be anti to each other. The groups are always going to be opposite each other. Good question. Yeah, that's a deep question. All right. If you have any more questions about that, raise your hands. Yeah, what's up? For, like, you mean the double bonds? It actually just depends on the bulkiness. So it actually doesn't depend on E1 or E2. It just depends on the bulkiness of your base. So if you have a super bulky base, you're going to go for the less substituted double bond because it's the only thing it can do. It can only grab those primary hydrogens. If it's not that bulky, it can get in and do secondary, tertiary, whatever. Okay, let's move on. If you have more questions about this, we can talk about it after. Please do come to me. It's super tricky, and it's a lot to absorb at the beginning. So ask away. All right. This problem with NBS and light. What do we know about NBS and light? It puts a bromine, next to what? Yeah, I heard the allylic position. What does that mean? So let's say we have this guy, and we use NBS and light on it. H nu is light. We're going to put a bromine on a carbon that's next to our double bond. We're not going to put it on the double bond. So this, let's zoom in on here. There's just some vocabulary we're going to go over. This carbon that's in the double bond is called the vinylic position. I'm probably not going to spell it right, V-I-N-Y-L-I-C, I think. Vinylic position. And then next door, let's change colors again, actually. Next door to that is the allylic position. And these are both allylic positions. And so NBS and light is going to put a bromine in that allylic position, one carbon over from our double bond. But in this problem, we have a bunch of different double bonds. How do you know where it's going to go? We actually need a little bit of a higher order understanding on this one. So what I'm actually going to do, we're actually going to do the whole mechanism for this guy. So let me get another page up. Okay. Make sure I draw it right. 1, 2, 3, 4, 5, 6, 7. whole mechanism. NBS is going to provide you with what? Yeah, bromine, but there's something special about that bromine. Bromine radical. It's going to provide you a low concentration of the bromine radical. So when you see NBS, just think it's a bromine radical. So let's go ahead and put that in there. We have our bromine radical. What that's going to do, it's going to abstract a proton from the allylic position. So from a carbon next to a double bond. So let's look at that. Here's a carbon next to a double bond. Is there anything over here? No, there's no allylic carbon over on the left here. So we're not going to do anything with that. We have one allylic carbon. How about this guy? It's an allylic carbon, right? It is. Yeah, it's an allylic carbon. But can we abstract a hydrogen from that allylic carbon? No, it's a quaternary carbon. Yeah, there's no secret hydrogen hiding there. There's already 4 bonds on that carbon. And can carbon bond more than 4 times? No, yeah, so there is no hydrogen in that allylic position. So there's actually only one allylic position hydrogen we can grab. I mean, kind of 2, but like, they're the same. So like there's 2 hydrogens here, and it's gonna grab one of them. So here's what we're gonna do. We're gonna form a new bond, single-sided arrow, remember, because it's a single electron. It's very important. Dr. Bean cares about that a lot. And that's gonna take one of the electrons out of that CH bond. Just one of them. So is this, as we have it, a sufficient mechanism? Do we account for all of the electrons? No, yeah, we didn't account for all the electrons. There's one more, actually, hiding in here. So there's 2 in that bond. There's 2 electrons per bond. We took one of them out. We didn't account for the other one yet. That other one is going to bounce back onto the molecule. It's going to stay put. It's going to generate a carbon radical. So let's go ahead and draw that. Now that we have all 3 of our arrows, all 3 electrons are accounted for, we're good to go. Let me go back to my blue. There we go. Now, we have this structure. What's going on here? Resonance. There's resonance here. So the radical can resonate with pi systems. Any pi bonds, anything like that, can resonate with those. So I'm going to draw the resonance contributors. I'm actually not going to do the arrow pushing for this resonance. Dr. Bean doesn't even do it on her keys. It's really messy with the single-sided arrows and breaking a bunch of bonds. What you have to do, you have to imagine that they're flip-flopping. So the radical's going to go over here, and the double bond's going to fill the space. So we're just going to switch them around. Double bond here, double bond here. So we just move the radical over. So that's one resonance contributor. Let's draw the other one. Let's say it goes the other direction. Let's say the radical goes over here. We're going to get this bad boy. Radical here, 2 double bonds on the left. Awesome. Can that radical here go any further? No, there's no more pi system for it to resonate with. The next carbon over is sp3, which leaves no unhybridized p, so there's no remaining pi system left. We're done. That's it. Okay, so we have these 3 resonance contributors. Now, what we're going to have, bromine, is going to come back in. We're going to have more bromine radical from our NBS. That's going to come in and react with each of these radical sites. And then, I guess if you want to draw another bond like that just to show they're forming a bond, that would be good. Remember bromine radical. Okay, forming a bond with all 3 of those sites. So all 3 of the sites that had a radical, they're now going to have a bromine. So what I'm going to do, I'm going to go back up to our problem. I'm going to put the answers in the boxes. I'm going to put a bromine. Notice where they end up. The radicals end up here, here, and here. So if you look at just one, they end up on this carbon, and this carbon. So for each of our 3 answer boxes, we're going to need to put a bromine in each of those places. Let's go back to our answer box. Okay, so we said on each of those dots, let's go back down and look, So we have, there's one on the left, then 2 carbons over, then 2 carbons over. Let's start with the one on the left. We added our bromine. Now we need to put the double bonds in the right spot. So they moved here, and they moved here. They can't go past here, remember, because that's the edge of the pi system. So now, let's do the one in the middle. Got a double bond on the edge here. Bromine. This is where our sp3 carbon was in the first place. Bromine's there now. Now we're going to put a bromine at the very end, towards that quaternary carbon. That's terrible. Let's start that over there. Sweet. Double bond here on the left, double bond in the middle, bromine next to the quaternary carbon. Any questions on that? Or how I got the bromines to be in those 3 places? Yeah, what's up?
So there's no minor or major?
On this one, there isn't any minor or major. There could be, because one of the radicals you generate, she may ask about major, like a major product or something for this. One of the radicals is primary, and then 2 of them are secondary. The 2 secondary ones would be very difficult to predict among, but what do we know about primary radicals? Really bad. Yeah, we don't want a primary radical, so that would definitely be the worst. The 2 with the radicals on secondary are going to be more often reacted with, because it's going to be in that state more frequently. So, just to reiterate, this product is going to form a little less than the other 2, just because it needs for that primary radical to be there. And it doesn't want to be a primary radical, it would rather be secondary on those. But she isn't asking. That's the nice thing, is that she's not asking, so we don't necessarily need to worry about it for this exam. That's just if it were a thing, if she asked, but she's not asking, so we're good. Okay, let's look at this. Number 3. We have CH3CH2S minus. Weak or strong? Strong, yeah, base or nucleophile. It's going to be strong, so if it's got that negative charge, it's almost always going to be strong. That is the first indicator of how strong it is. And what did we say about strength? What does strength indicate to us? It tells us the order. It tells us whether it's 1 or 2. So if it's strong, is it 1 or 2? 2. It's going to proceed by that second order mechanism, where the nucleophile or the base matters, because it's strong, so it should matter. What did we say also about trends in nucleophilicity with the periodic table? Do they get stronger going up? They get stronger going down. Yep, they get stronger going down. And S is below oxygen, right? So it's more nucleophilic than if it were oxygen. So think a nucleophile. And then also to the left. This right here is a strong nucleophile. Very strong nucleophile. It's not going to act as a base as much as it would if we had ethoxide. So if we had CH3CH2O minus, that's more apt to act as a base. The sulfur is more apt to act as a nucleophile. That's the big difference in trends, is that going up is more bases, going down is more nucleophiles. It's not a hard and fast rule. That's just a trend. That's something we can use to help predict. We need to look at everything involved. So now let's look at our substrate here too. Secondary. Can substitution happen on a secondary? Yeah, it's fine. Is it better than primary? No, yeah, primary is really what you want, but secondary is still totally fair game. Tertiary, not so much. Yeah, that's going to take an exceptionally strong nucleophile and maybe just CH3s on the tertiary site, maybe, but that's not even really that likely. So tertiary is definitely really not going to get some too. But we have a secondary substrate. Let's look here at both of these. Let's look at our leaving groups. We have bromine and Cl, chlorine. Which one is a better leaving group? Bromine, right. Bromine is a better leaving group. It's bigger. It's more apt to handle a negative charge. It has more orbital space, all of the above. It's just a better leaving group. But what do we notice about what it's attached to? The bromine. It's a double bond. How is it hybridized? sp2. Yeah, it's hybridized sp2. Sabrina mentioned this yesterday, and it's critically important. It will come up on your exam, guaranteed. Can you have SN2 on an sp2 carbon? No, you can't. There's technical reasons for why that's the case. If you're interested, we can talk. I'm not going to go through it right now, but just know no SN2 ever on sp2. That's hard and fast rule. We're not predicting, that's done. So even though bromines are better leaving group here, can it leave? No, yeah, the SN2 reaction can't happen there. Also, I think I kind of jumped the reveal a little bit and said that this was SN2. Does anybody have any questions about how I got SN2 out of this? I just said it was SN2, and I was gonna make a bigger deal out of it. But the solvent, yeah, that's a great question. So we have this solvent here, DMSO, and you need to know what that is. You need to either just memorize whether it's protic or aprotic or polar or not, or know what it looks like. This is what it looks like, by the way. Sulfur, oxygen, CH3. It's very similar to acetone, if you know what acetone looks like. But this sulfur here replaces the carbon. It's a very unusual compound. But what we need to notice about this is that there are no protic hydrogens. There's no, or I guess no acidic hydrogens, which means it's not protic. These CH3s, they don't count as protic hydrogens. It would be, say you had CH3OH, like more hydrogen bonding type hydrogens that could possibly be donated in an acid. That's going to matter. So this DMSO is polar, but it's aprotic. What did we say about protic solvents? Why does it matter? Protic solvents drive you more towards the ones. They're ionizing, and so they allow that leaving group to leave on its own. It stabilizes that anion, or that carbocation. So it allows it to leave. But if it's aprotic, we're not going to have any help towards the ones, so that's going to tend towards the twos. If you have no help with ionization, it's more likely going to be a second order reaction. So everything here is pointing to second order. This sulfur here is pointing more towards a nucleophile than a base. So if you know it's second order, and that it's probably a nucleophile, not a base, what do we have? SN2. We're good. Cool, cool. So we have SN2. What do we know about SN2 stereochemistry? What happens in the reaction? 100% inversion product. So since the leaving group doesn't leave beforehand, it's not attacking that planar carbocation where it can attack from the front and the back and give you a 50-50 racemic mixture. This is just going to attack one side exclusively because the leaving group hasn't left yet. It's going to kick out the leaving group. It's going to be a 100% inversion of stereochemistry. So let's go ahead and just draw, whoa, here's that, here we go. Go ahead and draw our molecule, Br. Now we have a wedge, we have a dash. So if our Cl was on a dash, and we have 100% inversion product, where are we going to put the S? We're going to put it on the wedge, yeah, to invert the stereochemistry. If we put it on the dash, we would be retaining stereochemistry, or we would have the retention product. We wouldn't change our stereochemistry. In this case, we want to put it on the wedge so that it's opposite from our chlorine. Our chlorine is on the dash. We want to put it on the wedge now. So we're going to have CH3, CH2, S. Sorry, S. And then what is left? What's the only other thing? Hydrogen. Yep, our hydrogen moves to the back. 100% inversion product, no reaction with the carbon holding the Br. If you have any questions, raise your hand. We can also talk after. Okay, there's our NBS mechanism. Moving on, number 4. So let's start taking things into consideration. Let's see what we got. What's our substrate? The bromine is connected to what type of carbon? Tertiary. Yeah, this is connected to a tertiary carbon. However, so tertiary might point you towards SN1 and E1 and all that. Let's look at what's on the arrow here. That bulky, or is it unhindered? It's very bulky. It has 3 ethyl groups on it. So it's a nitrogen with 3 ethyl groups on it. And 1 lone pair. bulky, I'll let you know too, it's very basic. It's highly basic. Remember that basicity increases going up on the periodic table, it's at the top. And also remember that basicity increases going left, I think that's left for you guys, left, and it's pretty left. It's further left than oxygen. So this is going to be a strong base. And even better, a strong bulky base. More detailed description. So we have a strong bulky base. What did we say about strength? Tells us the order, right? So if we have something strong, what order do we have? Second order. It's going to be one of the twos. And if it's a base, is it going to be an E or an S? E. We have an E2 reaction here. This is E2. So remember what I said about bulkiness and like the most substituted alkene and the least substituted alkene and all that. Let's look at our possible options here. Is that too many carbons? 1, 2, 6, yeah, it's too many. And I'm just going to put that. We've got our cyclohexane. All right, let's look at our two possible options here for elimination. We see our bromine was connected right here, correct? Yep, and it got eliminated. So it got eliminated. What else got eliminated? A hydrogen adjacent. So on one of the carbons adjacent to the carbon holding the leading group, this one, or this one of those got a hydrogen ripped off of it. And we're going to get different products depending on which hydrogen gets ripped off. So let's go with this one first. How many substitutions on that alkene? We have 1, 2, 3. And then there's a hydrogen, which we don't count for 4, so it's just 3. So we're dealing trisub versus, let's do this in orange here. Put the double bond there too, turning this to a CH2 now. How many substitutions on that alkene? 2. Yeah, we have 2. 1, 2. So 2 on the left side, none on the right side. So 2. So this is disub. So if you have no hindrance, if there's nothing stopping you, would you pick trisub or disub? You want trisub, so you want the more substituted alkene. You want that tri-substituted alkene. So you would go for this. If you're a super, super bulky base though, are you going to pick a primary hydrogen or are you going to pick a secondary hydrogen? You're going to pick a primary because that's all you can do. You can't get in there to get the secondary hydrogen nearly as well as you can just go to the very edge of the molecule and pluck off the primary hydrogen, right from the very edge. It doesn't need to go very far to get in. So even though our tri-substituted alkene is our more stable product, it's not going to be the major product because we're using this bulky base that just can't get in. It can't get in to get that secondary proton. So our major product is going to be that di-substituted product. And then our minor product will be the internal alkene, trisub. I'm not sure that this would come up in the exam or not. It may. So I'll go ahead and do it. This is called the Hoffman product. So Zaitsev's rule says that you go with the more substituted alkene. So conveniently enough, I probably butchered that. Is it Z-A-I-T-Z-E-V? That seems right. Zaitsev. We'll say it's right. The Zaitsev product. Zaitsev product is the most substituted. Hoffman product is the less substituted one. You're going to go for the Hoffman product with bulky bases. So terpetoxide and this, I'm not sure what to call it, I guess it would be triethylamine. Triethylamine, eh? Yeah, good enough. But it's a super bulky base, so you're going to go with the Hoffman product on that one. Any questions about that? Why I didn't pick the most stable alkene? Or does that make sense to everybody? Okay, good. Let's keep rolling. All right. Remember what we did last time with our whole chair conformation business? We're back. So we're going to need to do that again. So remember with chair conformations, do we want bulky groups at the axial or equatorial positions? We want them in the equatorial position. We want them away from all the action. Do we see anything on this ring that needs to be equatorial? Yeah, we do. Yeah, we have a tert-butyl group right here. And again, is that going to need to be axial or equatorial? Equatorial, yeah, we want this tert-butyl group to be equatorial. So that is going to be our starting position. Let's go ahead and draw our chair conformation. I'll draw it a little bigger than last time. It was kind of small. Okay, so we've got our chair. We want that T-butyl group to be up equatorial. This is just my favorite position for up equatorial. It's easy to find it. It's just the furthest one down. You can use any of the carbons that would give you up equatorial. So there may be multiple chairs that are the same chair and that are all right, but I'm just going to use this because that is an answer, so I'm going to use it. So we have our tert-butyl group that is up and equatorial. So everything up around the ring is going to alternate. So we have up, equatorial, right? Let's go over one carbon over this hydrogen. It's going to be up, right? Is it equatorial or axial? Axial. Yep, up axial. There's a hydrogen here. Is that going to be up axial or up equatorial? Equatorial, yeah. So up equatorial. So now we have this chlorine that's also on that same atom. We said, I didn't even draw the H, but we said that this hydrogen here was up equatorial. So if the chlorine is connected to that same atom and we already have something that's equatorial, what does it have to be? Axial. You can never have two things that are equatorial on the same carbon. You can never have two things that are axial, never two things that are up, never two things that are down. They're always going to be alternating. So this up equatorial hydrogen is connected to the same carbon that this down axial chlorine is. So let's keep going. Let's just double check all of our groups. So we have down axial here. So this is down also, right? This chlorine is also down. It's on an adjacent carbon. So is it going to be down axial or down equatorial? Down equatorial, yeah. So now what do we notice? We see we have two chlorines here. One of them is going to leave, right? Which one is it going to be? It's going to be the axial one. It's going to be the one that goes down axial instead of down equatorial because this T-butyl group, just to reiterate, needs to be in the equatorial position. So it is going to force the ring to be in a certain conformation almost exclusively. So only one of these chlorines is actually any good in an elimination reaction. Again, I jumped the gun and told you it was elimination. Let's look at our arrow just to confirm. So we have CH3O-. Strong or weak? Strong. So is it going to be 2 or 1? 2. It's going to be one of the 2s. Is it a base or is it a nucleophile? Base. Yeah. In this case, so it could act as a nucleophile. More likely it's going to be a base. Let's look at an example where it would be a nucleophile. Right here, with this primary substrate. On a primary alkyl halide, this will actually substitute. In any other circumstance, though, methoxide will eliminate. So only on primary alkyl halides, or methyl like bromomethane, or whatever, something like that, like methane or primary, is going to be a substitution. Anywhere else, so say you put the bromine here. Now is it going to be substitution? No. Yeah, so now it's going to behave as a base. So the only time really you're going to see something like CH3O- behaving as a nucleophile is on a primary site. Primary substrate, primary alkyl halide. That's all. Every other case, E2. So we know this is E2. Yeah, what's up? Sorry, what was that? It can vary between base and nucleophile. It depends on a lot of things. So there's not really one factor that I could give you where it's like, this will tell you whether it's going to be a base or nucleophile, besides the one that I just gave you. That's really the biggest hint I can give you. It'll behave as a nucleophile on a primary substrate. So this can still be a strong nucleophile if it's a primary substrate. Every other case, strong base. I'm not sure if I answered your question. Come talk to me after if you're still curious. Cool. So we know only one of these is really going to eliminate. I'm going to erase all this garbage. So now we know this is the chlorine we're after. This is not the chlorine we're after. Because this is equatorial, this is axial. That's what we want. We want it to be axial. So now we have that axial chlorine. We need to find a hydrogen on an adjacent carbon that is trans and also axial, trans-diaxial. We need to fulfill both of those requirements. So let's look next door to the left first. We're looking at this carbon to see if there are any hydrogens on there we can abstract. Are there any hydrogens on there? No, so the trans-diaxial thing doesn't even matter. There aren't even any hydrogens. So that's already done. Yeah. Now let's look one carbon this way, to the right, or counterclockwise, if you will. Two hydrogens on there. One is going to be up, one is going to be down, one is going to be axial, one's going to be equatorial. Let's pick this one up, the up hydrogen, the one that's trans. Is that going to be axial or equatorial? It's axial, yeah, because remember, the thing that's up next door was equatorial. We already said it had to be equatorial. So anytime you move carbons, it's going to alternate. So up equatorial on the left here, up axial when you move one carbon over. So that's axial, axial, good, up, down, trans, we're good. Trans-axial, we're set. So we know our double bond formation is going to happen here. There were a few possible options, we just narrowed it down to one. That was that whole process. So let's go ahead and draw our final product. We have our hydrogen. We have our terbutyl group, CH3. Do we have our Cl here on a wedge? Is that right? No, yeah, what happened to it? Got eliminated. Yep, E2, it eliminated, so it's gone. Also, a hydrogen here got eliminated, so those are gone. What is now taking their place? Double bond, so there's now a double bond here. We formed a double bond. We know nothing happened to the bottom carbon, so we're just going to redraw that, if I can even draw. There we go. Not draw this wedge. I don't know what the deal is. CH3. Cl. That's the only possible double bond that can form. The chlorine at the bottom here, it's stuck in an equatorial position for almost the entire time. So almost exclusively, it's stuck in the equatorial position. You mean like of these hydrogens here? Or you mean, yeah, like in this spot right here? Stereochemistry would go away. Yep, because those are sp2 carbons, and that's planar. What's up? Difference between a nucleophile and a base? The biggest difference. So just to reiterate what the big difference is between a nucleophile and a base. Let's talk about that. So the biggest difference is the trend for nucleophiles. Nucleophiles get stronger going down. Bases get stronger going up. That's the main difference. There is some overlap. There are molecules that can behave both as bases and nucleophiles. You're going to have to look at the substrate, you'll have to look at the solvent, you'll have to look at a number of other factors to decide whether it's going to act as a nucleophile or electrophile. The biggest first thing you should do in predicting is look at the strength. That's the most important thing you can do. Look at the strength, because that automatically narrows it down to a 50-50. If it's strong, it's going to be one of the twos. If it's weak, it's going to be one of the ones. So you've already narrowed it down to 50-50. That's great. Read those pages too. That gives you a much more detailed guide. This reaction, also not on your exam. Dr. Bean emailed me and said no for this. This is an elimination that forms an IBR bond. It's very weird. It's not on your exam. Don't worry about it. So good on that. We don't have to do that. Okay, mechanism. We have 3 products. So this is going to get crazy. Let's look here and see what kind of reaction might be happening. So, looking just at our products, we can kind of see what's going on here. So, in this first one, let's just focus in on this first product. Do we have any new double bond formations? On the first compound, our first product, any new double bond formations? No, so there's not going to be elimination that leads to that pathway. Do we have a new group on there, a new substituted group? Yeah, so the first product, that first pathway, is going to be the result of some kind of substitution. Let's look at the next 2. Just this next one. Any new double bonds? Kind of yes. There's still just one though. So it's not really new, maybe just moved. We'll talk about it. But there isn't another double bond. So is there elimination happening for pathway B? No, yeah, for that second molecule there, that's not going to be an elimination, it's going to be a substitution. So we have that new group there too, the OCH3 that wasn't there before. So there was a substitution there to put it there. Now let's look at this one. Do we have another double bond? Yeah, so there's going to be some elimination going on there. So notice we have a combination of substitution and elimination. What does that kind of hint at? I mentioned it earlier. It's probably going to be first order. Hopefully it makes it. That'd be really sad. But anyway, so we have 2 substitution products, 1 elimination product. If you have a mix like that, it's probably first order. SN1 and E1 typically go together. Let's confirm our suspicions. Let's see if there's anything else that can help us out. We have CH3OH. Strong or weak? Weak. What does that tell us about the order? First order. We pretty much already confirmed it. So that's great. The heat is going to help the leaving group leave. It's not really a solvent, so it's not going to help us any with that. Let's go ahead and do the first step. So the first step for both E1 and SN1, are they the same or different? Same first step. What's that first step? Leaving group leaves on its own. Doesn't need any help. It's just gonna leave. So step 1, electrons get kicked off onto the bromine. That leaves a positive charge behind, remember, and the negative charge goes away with the bromine. So let's go ahead and draw that. So leaving group leaves. You don't need to write these on your arrows. I'm just kind of giving you a little guide of what I'm doing. But you can just draw your arrows. So leaving group leaves. And then it didn't leave. So let's make it leave. Okay, so now we have our carbocation. Great. So one thing that is common with our first order reactions, when our leaving group just leaves on its own and you've got a carbocation, there are rearrangements that are possible. Those rearrangements will happen if it gains stability by doing so. So let's look at what might make this more stable. We have a secondary carbocation, right? Could that be better? It could be tertiary, right? Is there anything we can do that would make this tertiary? There's a hydrogen here, there's going to be a hydride shift. What's going to happen here? This hydrogen and the electrons in the CH bond are going to hop over to the carbocation. Is that going to be a carbocation anymore, that secondary carbon? No, yeah, so the carbocation went away. And it went onto that tertiary carbon right there, where the hydrogen left. Notice this bond broke, and the carbon holding that bond lost electrons. They went with the hydrogen. hydride shift. Remember I said this grants stability. These rearrangements happen when it grants stability, because it takes some energy to do that. It won't do it unless it's going to be good, unless it's a good thing in the end. So let's look to see if it was actually productive. We have a secondary carbocation, now we have a tertiary carbocation. Better? Better. That's why that rearrangement occurred. To be more stable there. Let's look too at our products, just in case we weren't sure what was going on. Notice, let's just look at our first one. Look at the carbon that got substituted. Is that the carbon holding the leaving group originally? No, yeah, so it's substituting at a different carbon where the leaving group, than the one where the leaving group was. Sorry, that's kind of tough to word. But like, it's on a different carbon. It's substituted at a different place. That's a great indication that some sort of rearrangement happened. Because if the leaving group just left and then it substituted, it would be on the same carbon. But it moved. Yeah, it's on a different carbon here. This CH3OH didn't substitute here. Does that make sense? That's a good hint that you're going to have some rearrangements. Okay, so we've got our hydride shift. Now we have our tertiary carbocation. This is where it diverges. Let's just do something. Let's pick something to do and do it. Let's do a substitution reaction at the carbocation. There's a number of things we can do. Let's just do that one. So we're going to substitute at the carbocation. Let's say, call this A, call this A. And I'm going to say redraw. That I'm not sure necessarily is required. I'm just showing, just to be ultra clear, that I'm just redrawing this compound. Just so we have a little bit more space to work with. Okay. So there's our compound. We said we were going to go ahead and substitute at that carbon. It's going to be our SN1. So we have, what was our nucleophile? CH3OH. See, in this case, it's acting as a nucleophile. On the others, it's going to act as a base because it's elimination. So we're going to substitute, it's going to be a nucleophile. CH3OH. 2 lone pairs, neutral charge. That's going to go ahead and attack the carbocation. Do we need to show stereochemistry? The answer doesn't show it, so no. If the answer doesn't show it, don't worry about it. You don't need to, because it says, provide clear mechanisms to explain the formation of the products shown, and the products shown don't have stereochemistry, so just don't even worry about it. So CH3OH is going to attack that carbocation. Remember, charge is conserved, so it might not go away yet. Double bond at the end, methyl up there. Now we have our new group, OCH3. Did that proton leave yet? The one that was here on the CH3OH? It's not gone yet. So it's still attached. I know, right? That positive charge is going to be on the oxygen. Oxygen has how many bonds in this one? 3 bonds. Is it used to 3 bonds? No, it's used to 2. So if it has 3, it's going to have a positive charge. So now what we need to do, we need to have a base come along and deprotonate that. The only thing floating around in solution is our CH3OH, the one we just used earlier. That's going to come grab the hydrogen, form a new bond with the hydrogen, and take the positive charge with it. The electrons in this OH bond right here, are they going to go with the hydrogen or are they going to go onto the oxygen? Onto the oxygen, they'll flow towards the positive charge. They're going to go onto that oxygen. And then that will form our product A. Like, do we need to show this step? Yes, you do. So, this last deprotonation step is worth points. You can't miss it. You have to show everything that happens. And every step, don't do the deprotonation and your nucleophilic attack in the same step. Because what happens, the steps of this, so far, leaving group leaves, hydride shift, nucleophilic attack, and then deprotonation. So we need to show all 4 of those as separate steps. What's up? Yeah, no. ER minus. Yeah, I think you can. It's a lot more likely for the methanol to come by and do it because there's so many more of them. There's tons of them, probably billions. And this leaving group leaving is going to generate, a 1-to-1 ratio of Br minus to the molecules you're interested in versus having like a 1,000,000,000 ratio. So it's more likely for the methanol to do it. Good question. So we have shown product A. I'm just going to call this one A. Erase some of this craziness. We're going to call this one A. And this pathway just led to the formation of A. That's it. We need to show now formation for B and formation for C. So let's go ahead and do that. Let's now redraw for B. I'm going to redraw it. Here are these. We've redrawn it. Great. Let's look at B. Let's see what needs to happen here for B. So notice our double bond in product B up here, product B, the double bond moved from its original location. So what might be going on that makes that happen? Resonance, yeah. So now, after that hydride shift, our carbocation is next to that double bond. It's next to the pi system, so it can resonate with the pi system. How are carbocations hybridized? sp2, always. So they can interact with the pi system. So right here, we're going to show some resonance. With carbocations, you use your door swing. That's not the whole one we went over where it was lone pair to bond, bond to lone pair. That's anions. Cation resonance looks like this. It's like a door swing. Door swing. And that's for positive charges, cations. So we're going to show here our arrow, double-sided arrow. This is resonance, right? So our double bond moved locations, right? And it put that carbocation in the primary position. Good or bad? For that carbocation? Bad, actually. It's bad. It's not great. But we just need to show the pathway for this formation. So it doesn't even matter whether it's good or bad. That's what the product is that she wants us to get. So we're going to react with this anyway. Because that's what she wants us to do. That's really the only answer. Because Dr. Bean says so. So that's what we're going to do. For the mechanism section, it's great to constantly be going back and forth between what you have and what you need to make. Because she's given you the products. She's given you what you need to make. So it's a really useful thing to have on hand, knowing what you're supposed to come up with. So we know we're supposed to react with that, even though it's not the best one. This can be the major contributor, but we're going to react with this one. So let's go ahead and do that. The reaction that I'm talking about, what kind of reaction is it for B? Substitution or elimination? It's going to substitute. Yeah, there's a new OCH3 there. So let's put that bad boy on there. CH3OH, lone pairs. We go attack our carbocation. That's our electrophilic site. So our nucleophile attacks our electrophile. Close out our resonance brackets. Let's put that down here. So we have the double bond stayed there, and we now have another group instead of that carbocation. We have our OCH3. Anything missing? We have to show the deprotonation step. That proton on the H right here, let me actually just go ahead and color code that so y'all can see for sure what I'm talking about. It's this H right here. You need to show where that goes. It doesn't just magically disappear. So we need to show another base coming along, CH3OH, with its lone pairs, grabbing the hydrogen and dumping the electrons off onto the oxygen that was positive. Don't forget to show that positive charge. I just forgot it. Don't forget that. That's very important. Show all formal charges. Make sure they don't disappear. Charge is conserved. So now that we've deprotonated it, do we have our product? Do we have B? Yep, so we're just going to say we formed B. We're good. That's done. Are we done with this problem yet? No, this is a long one. We have to do a third one. Let's look at product C. What kind of reaction are we going to have to do? Elimination. We formed a new double bond. Right there, that guy. We're going to need to show the formation of that. Let's redraw again for C. Again, that's just a redraw. There was no chemistry step there. So, here we got it. We know we need to create a double bond here. That's our goal, right there. So, we have a carbocation. We need to make it here. We need to make that double bond right here. Where are we going to abstract our proton from? We have a few options. This carbon, not really that carbon, so it's just those two carbons. We're going to go the bottom one or the top one? Bottom one. Yeah, the bottom one is going to give us the double bond we need. Of course, I just erased everything. So we're going to go with this hydrogen right here. Because that's going to form the double bond right there. We can't go with any other hydrogens. So let's do that. CH3OH, just like before. So it's going to attack our electrophilic site, right? What do y'all think? Is that right? No, not for this step. That would be a what kind of reaction? That's a substitution. Don't do that. We want to eliminate. So we're going to go grab this proton. And that is going to kick the electrons from the CH bond in between those two carbons. They're going to go towards that positive charge. They're going to create a double bond. Do we need to show a deprotonation step? No. Yeah, everything's already gone. Yeah. So we actually now just end up with C. We're good. That's it. Any questions about that? Any questions about mechanisms in general, like the format of the exam? Yeah, what's up? Asking, on the elimination, so on this molecule C here, do we have to do the hydride shift first? I would think the answer is yes. I would do the hydride shift first because the hydrogen's already right there. The carbocation's already right there. It doesn't need to wait for the base to come along and collide. The hydride shift just happens internally. It's just inside the molecule. So the hydride shift's going to happen first. We're not going to eliminate from here. I do think it is possible, but I think the hydride shift is going to happen first. And I think that's the mechanism she's looking for. So that's a great question. All right, let's move on to synthesis. Synthesis is super fun, especially in Orgo 2. So this is going to get cool later, I promise, even though it doesn't seem like it. Okay. So, with synthesis, the beauty about synthesis problems, especially this early on, that there are very few reactions that you really need to know for this. There are common themes. She uses the same reactions every time, every year. So if you practice 3 or 4 synthesis problems, you'll start to see that you're using all of the same exact stuff. You're going to use NDS in light a lot. You're going to use BR2 in light a lot. You're going to use SN1 a lot. Those are really the common themes for this test. If you do 3 or 4 of them, you'll start to see for yourself. Let's go ahead and jump right into this. This is retrosynthesis. So what you get is the final product. You are given the final product. You need to work backwards to get down to tiny pieces. So what you're allowed, let's read the directions. Synthesize the molecule below from alkanes of 4 carbons or less. So we need to break this guy down into alkanes of 4 carbons or less. Are we allowed alcohols? Are we allowed alkenes? None of the above. We need to go all the way back to just pure alkanes. Also notice we can use any inorganic reagents. For example, that would be like NaSH or NaOH, which might provide us with the sulfur or oxygen we need to make our final product. Those are inorganic reagents that we can use. Also, like NBS. That's interesting. NBS is organic. But you can use NBS, I promise. You can use NBS, that's totally fine, even though it's organic. I don't know why, but anyway. NBS counts as something you're allowed to use. NBS and light. So we know we need to break this down to 4 carbons or less. Let's look at this molecule. So we have, right here, there's 3 carbons. That's below 4, right? 4 carbons or less, so that's fine. We could break that piece. And then we have 1, 2, 3, 4 carbons on this side. So that's great. So we have kind of chunks of 3 and 4 here. So we know we're going to need to kind of bust this in half right across the oxygen. One of the groups is going to have the oxygen on it, one of them won't. What can oxygen do like that might form a bond here or here? Could it substitute? It could, yeah. So there's probably going to be some substitution reaction where you're making use of oxygen as your nucleophile to substitute something. That's what's going to combine these 2 pieces together. You need to start kind of making a game plan before you just jump into this thing. So another thing we notice, we have this Br here. What's the Br next to? Notice. That double bond. So we have a Br2 next to a double bond. Does that ring a bell? NBS and light. Yeah, she's going to use it a lot. You'll see it a lot. So let's actually just do that right away. Let's go ahead and take care of that. NBS and light. And remember, this is going to put a bromine next to your double bond. So this bromine wasn't there before. We put it on. We just put it on with NBS and light. Why not Br2 and light? Br2 and light isn't stereospecific like NBS and light is. Br2 and light will just kind of throw it anywhere, particularly on the most substitute position. NBS and light is specific to that position next to the double bond. So we've got this now, broken that away. So now we have the task of busting this in half. So we have 2 options. We could try this. And that. So here our leaving group is on a primary substrate. And then here, both of those substitutions would make our product. Which one's better? Are we using, what kind of reaction are we using? We have weak, notice, weak base, weak nucleophile, so it's going to be one of the ones, and it's a substitution. So we have SN1. Yeah, this is going to be an SN1 reaction. So what's that first step of SN1? Leaving group leaves on its own. Which one of these is the leaving group more likely to leave on its own? The one on the right, actually, puts that bromine on a secondary carbon. So you're going to generate that carbocation much more easily. So we're going to go with the one on the right. We want the bromine on that secondary carbon. Br, because that's going to leave. And then we have HO. Why didn't I use the strong one? Why didn't I use O-? The real reason is because you don't know how to make that yet. You can't really just like throw in OH, like some random base, and expect it to deprotonate and everything is great. It's probably going to start reacting is what's going to happen. So there's like very specific ways that you need to make this, and you haven't learned them yet. So if you pick something like that, and you have no idea what to do with it, no idea how to make it, there's probably something else you can do. There are multiple answers to these types of problems. So if you get to something like this and you have no idea how to make it, try something else. Stick generally for this exam with SN1. Stick with SN1. Go with the weak one, because this is much easier for you guys to make. So we add these two together. We make our products. Is there anything else we need to show? Heat. SN1 and E1 reactions require some heat in order for the leaving group to leave on time. So we're going to need to show that heat. That will lose you points if you don't show it. I'm going to move these a little further down. Give myself some room. Okay. Do we want to synthesize the left or the right first? Let's go left. I heard kind of both, but it doesn't matter. We're going to have to do them both. So let's go to the left. So we have this Br on a secondary carbon, two primary carbons. What reaction do we know that puts a bromine on an alkane? Br2 and light. That's the very first reaction you guys learned. So we're going to put Br2 and light. H-nu. You can say H-nu or light. You can write the word light. They're both fine. And that is going to give us propane. Are we done on that side? Yeah, we're not quite done. That is it. That's the bottom. We are allowed alkanes of 4 carbons or less. So that's propane. It's an alkane and it's 4 carbons or less, so we're great. The only thing we need to say is that we need to use an excess in this. So that is 2 points for your exam, just so you know. That's 2% of your grade, putting 2 letters excess, just so you know. So put this. Don't forget it. If you use Br2 in light, anytime you use Br2 in light, put excess. Don't just put excess on everything, though. She will take points off if you say excess when you don't need excess. So know that so just this Br2 in light reaction, that's the only one you need to know, use an excess, because you don't want to risk forming this. That's the reason. You don't want to dibrominate. And this reaction is capable of dibromination, so you don't want that. So we need to say that we're using an excess of propane. That's it for the left. The right looks a little tougher. There's a lot going on. So we have this OH here. It's connected to a primary carbon, so we could substitute that on there pretty easily. It's connected to a primary carbon. So if we're going to substitute that on there, we're going to need a leaving group to kick out, right? So let's go ahead and redraw this thing with a leaving group that we kicked out before we worry about the reagent. So we know that we kicked out something. Pick bromine. That's what I would always do. Pick bromine for your leaving group. So you kicked out bromine. What reagent did you use that put an OH on that thing? I would use NaOH. This would be an SN2. This would be either a strong base or a strong nucleophile. But remember what I said about primary alkyl halides. Is it going to be a nucleophile or a base? So if it's a primary alkyl halide for the substrate, this is going to act as a nucleophile. Because remember, when it's on primary, it can just get in there and do that. But secondary or tertiary, there's too much going on and it's going to eliminate. Those protons are much easier to grab. So this NaOH here, that's going to be an SN2 reaction. And this is your nucleophile. Your OH minus is your nucleophile. It's all right. So that OH is going to go in, substitute the bromine. Awesome. So now we have this compound here. Bromine is next to a double bond. Ring any bells? We should use Br2 in light, right? Right? No, not right. Yeah, we don't want to use Br2 in light here. It's next to a double bond, so what do we use instead? NBS in light. That's the one that's specific to double bonds. So don't use Br2 in light here. Notice how there are trends. So you've got, you create a nucleophile for SN1, go back to Br next to a double bond, NBS in light. Same thing kind of happened over here. So it's like you're going to have trends that you'll see. This exact sequence of reactions shows up about 8 times in old exams. Exactly the same. So literally, there are themes that come back every time. So just practice about 6 or 7 of these, and you'll be set on synthesis. Not for real, just do it. Yeah, it doesn't take that long. So NBS in light, that's going to put a bromine next to our double bond, right? We have our double bond, and the bromine went next to it. But this is retrosynthesis. This is what was there before we did that NBS in light step. Now we have to make a double bond. What reaction do we know that makes a double bond? Elimination. Yeah, so we're going to use an elimination. I prefer E2. E2 is much easier. You're not going to have very many side products and all that. So what's a good reagent for E2? There's one that should come to your mind instantly. Tert butoxide. Yep, E2, tert butoxide works really well. So we're going to use tert butoxide. And you can say O-. Typically, it's potassium tert butoxide, like if you get it in a bottle. So you can say it like that. So we use tert butoxide on this thing. It's going to cause an elimination reaction to happen. And either of these two would give you the correct product. Either of them would actually give you the correct product. So you could use this or you could use this. Which one would you rather use? There is a right answer to this. Yeah, so top, do you want the top one or the bottom one? You want the bottom one because that's much easier to make. So if you have just this by itself, and you use Br2 and light on this with your excess, Br2 and light. If you use Br2 and light on that, where's the Br going to go? On the tertiary carbon. It's not going to go on the primary carbon. Remember that? It's going to go to the most substituted site. So your Br is going to go there. That's really easy to do. This takes like 6 steps. I tried it. It's annoying. Don't deal with it. So just don't do that. You'll want to use the one that puts the bromine on a tertiary site. That's still fine with tert butoxide because there are primary carbons that it can grab the hydrogen from. So it's no big deal. So we have bromine on the tertiary carbon, not the primary. Anybody have questions about why we decided that one? Cool. All right, so now we already said how we form that, Br2 in light. And we're done. Are we done? Is that all? We good? Excess. Yes. Don't forget excess. That's 2% of your grade. That would really suck if you got 100 on the exam except for that. 98. Or even. That's it for synthesis. I want to go back and hit those nomenclature problems. Before we do, does anyone have any questions about what we've gone over so far? ahead and double back and do those nomenclature ones I skipped. Go ahead and raise hands, I guess. Yeah, so if you still have questions, raise your hand. People will come around to you. I'm going to go ahead and double back, and we'll get some nomenclature done, and then I'll be free to answer some questions too. So, let's actually just pick one or three. I don't feel like we need to do more, unless you really want to do more. Do you feel comfortable on one? RNS? Let's go ahead and do one. Let's do one. Okay, so stereochemistry. Let's talk about RNS. So, we're going to need to assign RNS for every chiral carbon we have in our compound. So let's look at number one. How do we know that something is chiral? Hey, if you're leaving, just keep it down so that people can hear. It's pretty loud. So looking at this first carbon, how do we know that a carbon is chiral? How do we know? It has to be attached to 4 distinct groups. So let's look. Typically, the carbons in the middle here are going to be the ones that are chiral, if they are. So let's look there first. Let's see if they're chiral. So let's look at the top one. We have a Br, we have a C, and a C. So there's 3 carbons, but those 3 carbons have to be equal if it's a chiral. So if they're all distinct carbons, then it can still be chiral. So let's break the tie. This C is connected to a Br, a C, and an H. Why does this keep happening? Sorry, guys. This carbon is connected to 3 H's. This carbon down here is connected to a Br, a C, and an H. Uh-oh. Why? I'm not saying hey Siri. I don't know. It's at 31%, so it should be okay. But looking at the top and the bottom, we have a Br, C, and an H. And at the bottom, and down here, we have Br, C, and H. So these still could be the same carbon. We have to go out one more. This one, now H, H, H. This one, C, C, C. So now we notice that they're different. We see that they are in fact different. Even though right at the beginning we thought they might have been the same, they're different. So this top carbon is chiral. It's attached to 4 distinct groups. Let's look at the lower one. Do you guys have questions about determining whether something is chiral or not? Does that make sense? Okay, the bottom one's chiral. We're not doing it. Surprise, it's chiral. Are there any other chiral carbons in here, actually, just for fun? There is one more, actually. It's hiding. Yeah, that top carbon there is actually chiral. You're not given any stereochemistry, though. Like, you're not given what the configuration is right here. So you don't need to show stereochemistry. Even though that's chiral, you don't need to show stereochem there because of this whole thing where it's be sure to include the stereochemistry where appropriate. You don't know what it is. It's not given, so you don't need to worry about it. I guess she decided 2 was enough. She was being nice. So, let's dig in. That was a C, H3. I redrew both of these so that we would have one for each chiral carbon. We're now going to figure out the RNS configuration. What we're going to do, we are going to assign priorities to every group connected to the chiral carbon. And we're going to do that by atomic number, which is like atomic mass, same thing. So let's look at this red one, the top carbon first. So connected to it, we have bromine. Is that going to be our highest priority thing? Yes, bromine is a really high atomic number. I don't know it off the top of my head, but it's pretty high compared to most of the organic compounds. So this is going to get our first priority, priority 1. Looking at the other things, we already looked at them before. They're all carbon. So carbon all has the same atomic number, right? We're going to need to go off what those carbons are connected to see where the priority goes next. So let's look at the top one first. We did this already, but we have a Br, a C, and an H. This left one, H, H, H. So did it automatically just lose? Yep, it did. Connected to 3 hydrogens, that's going to lose. This next one, Br, C, H. We're tied. We have to go another carbon down the line. Because see here, this carbon and this carbon are attached to all the same stuff. So we're still tied. We need to go one further to break that tie. So now we look at what this carbon is connected to, and we look at, or sorry, we're looking at the next carbon, H. Now we're looking at this carbon versus this carbon, because we have to go one further, because we have to break the tie twice. So now we have attached to the top H, H, and H. To the bottom we have C, C, and C. Now we finally broke our tie, right? The first point of difference is several carbons away, C versus H. That's our first point of difference. So the bottom carbon here is going to win. Second priority, third priority, and then fourth priority is this methyl group here. Erase some of this so we have a little more room to see that. We're going to do that. Okay, there we go. So now we have our priorities. What we're going to do now, we're going to draw an arrow from the number 1 to 2 to 3. We're going to ignore 4. Arrow 1 to 2 to 3. Right? Is it clockwise or is it counterclockwise? Counterclockwise, which means R or S, means S. So we have S stereochemistry. Looking at this carbon, the fourth priority though. Looking at that fourth priority, is that on a dash or a wedge? It's on a wedge. Remember with Fisher projections, we have our bow ties, remember? So the sides are going to be wedges. So do we want our lowest priority group to be in the front or in the back? We want it to be in the back. We want it to be on a dash, and that's just conventional. What we do when it's not, we flip our answer. So this is in front, so we're going to flip our answer as a result. Because what we just calculated is the reverse stereochemistry. We just calculated it as if it were in the back, but it's not, so we're going to have to change our answer. We had S, but we were wrong, because this carbon was in the front. We're going to change our answer to R. So that first carbon we just did, the stereochemistry is R configuration. Let's move on to the next one. Do it a little quicker. Highest priority bromine. We have a hydrogen, that's automatically going to lose. That's our 4. Now we have to break the tie between 2 carbons. This carbon up top, here's a good question actually. So this carbon up top is connected to a Br, a C, and a C. It was less of a good question than I thought actually. But this one's connected to a C, a C, and a C. So which one's going to break the tie? Top one, bromine. So this carbon up here is going to have a higher priority than the other carbon. Is it going to have number 1 priority? No, you were just breaking the tie between 2 and 3. So we're going to have 2 and 3. What's our next step? Draw an arrow from 1 to 2 to 3. We're going to draw 1 to 2 to 3. Clockwise or counterclockwise? Clockwise, is that R or S? That's R, yep, R. Look at our fourth priority. Is it in the back? No, so what do we do with our answer? We flip our answer because we just did it wrong. We need to flip our answer so we got it right. To S. We have S stereochemistry on that bottom card. Okay, so we just dealt with the stereochemistry. We haven't even started numbering. What's the very first step in any nomenclature problem? Yep, find the longest carbon chain that contains your parent functional group. In this case, it's an alkane. That's the highest priority thing you got. So we're going to find the longest carbon chain. It looks like top to bottom, because there isn't very much going on the sides. So we can call this 1, 2, 3, 4, 5, 6. Right? These two, the 2 other ones are sticking off of 5. Everyone kind of see that? So 6 carbons. We know it's an alkane. So what's our parent name here? Hexane. That's our parent. Now there are a lot of substituents on here. Let's go and break it down. So we have 3 bromines. Let's just look at the bromines for a second. Actually, first thing, let's look and make sure we have the right numbering order. I just picked a direction, but we need to make sure that that's the right direction to go. It could go top to bottom, 1, 2, 3, 4, 5, 6, or bottom to top, 1, 2, 3, 4, 5, 6. We need to put the substituents on the lowest numbers. So going the way I picked, let's just look at that. So we have a substituent on 2. We have 2 substituents on 3, 3, 3. We have a substituent on 4, because see on 3 we had bromine, CH3, 4 there's bromine. So we have 1 on 4, 2 on 5, 2 methyl groups there, nothing on 6. So that's our first numbering. Let's go the other direction now. Just switch it up. 1, 2, 3, 4, 5, 6. Now let's look and see where our substituents are. So do we have any on carbon 1? Nothing on 1. There are 2 things on 2. We have something on 3. We have something on 4 twice. And we have something on 5. So, are you going to add all these numbers up and see which one's lower? No. You're going to look at the first point of difference. It's always the first point of difference. So, let's look. First one, tie. Second one, first point of difference. Which one wins? Are we going for the big numbers or the little numbers? Little numbers. So we want orange. We're going to go with orange. So we're going to name this from the bottom to the top. Because we want those substituents to have the lowest possible numbers. If your numbers here, if your series was tied, then what would you do? Then it would go to alphabetical order. You would want to put the substituent that comes first in the name at the lowest number. That's if these 2 series of numbers here, if they were completely perfectly tied, then you would go to alphabetical order. In this case, they're not tied, so we're done. We're going to go with the orange way. Okay, so now let's look at our subs. So let's look at the bromines first. We know it's going to be bromo, right, for substituents. We have 1 on 3. We have 1 on 4, right? And we have 1 on 5. What do we need to do to this bromo to indicate that we have 3 of them? Say tribromo. 3, 4, 5, tribromo. That's all of our bromines. So we got that, we're good. Let's look now at any methyls we might have. So look here at our T-butyl group. Where are the 2 methyl substituents? One of them is part of our parent. So there are 2 methyl substituents on the second carbon, right? So if you look at the T-butyl group kind of at the bottom here, see the C, there's 3 CH3s coming out. One of them is a part of the parent. 2 of them are substituents. So we're going to need to put those 2. So we have a methyl on 2, another methyl on 2. Let's keep going. Do we have any more methyls? On 4. So on 4 we have a methyl. Any others on 5 and 6? No, we're set. So we have 3 methyls. What do we need to do to indicate we have 3? Trimethyl. Any other substituents here we need to indicate? Any ethyls? Any other halogens? Nothing. That's it. We're good. So we're ready to name this. We have our stereochemistry, which I think is the first thing you should do. We have all of our substituents. We have our parent name. We have no complex substituents on this thing. So we're ready to go. Where do we put stereochemistry? At the very beginning. That's the first thing we're going to say. So we have an R and we have an S. We need to indicate which one's which. We can't just say RS as R. Something like that. We need to actually say where they are because you have multiple centers. So you need to say which one you're talking about. So the 2 stereo centers were at 3 and 4. What was the stereochemistry for carbon 3? 3s. And then what was it for carbon 4? 4r. So now, when you alphabetize, do you alphabetize with the T, the tri? No, you actually just skip to the first letter of your sub. So it's B versus M. Which one's going first? Anybody? B. B's going to go first. So we have 3, 4, 5, trimethyl, bromo. After all that, bromo. 2, 2, 4, trimethyl hexane. I'm kind of hesitant to put a dash. The thing you need to know is that the trimethyl and the hexane, all one word. There's no dash, there's no nothing. I just needed to move it down because I was running out of room. But that's all one word. No dashes, no spaces. Cool. Any questions on that? What's up? Shout loud.
Yeah. So if you have a parentheses right before you start the parent chain, do you need a dash there too?
It depends on whether or not you have a number at the beginning of the parenthesis or not. So say for example, so you had 4 dash. Are you saying like when do you need this dash?
No, like you need a dash like between the parentheses when you start writing your parent chain, like there just needs to be a dash there as well.
Oh, like after for the parent. No. Unless you have some numbers. So when you use dashes to indicate that you're changing from a number to a letter. So like notice in our answer here, we have 3s4r dash, now we're on numbers, dash, now we're at letters, dash, now we're on numbers, dash, now we're back to letters. So you're just showing that you're changing back and forth. The dashes are for, hey, now we're on numbers, and then that relates to this thing. Hey, here's more numbers that are, those are related to this thing. So it's like that. Does that answer your question? Good, sweet. Any other questions on this? Cool. Let's do number 3. Do you want to do number 3 or? Cool, let's do it. So what's our parent functional group here? The alkene. Yeah, alkenes take priority, right, over alkanes. They are higher priority. So we are going to find the longest continuous carbon chain that has our parent. Can we count rings and linear chains together? No, we have to count them separate. So if the ring is the biggest, we'll go with the ring. If the linear chains are the biggest, we'll go with the linear chains. But you can't combine them in your numbers. So let's look. We have a linear chain of 2, linear chain of 2, and then a ring of 6. Ring of 6 is going to win, and it contains our parent functional group. Win all around. So great. We're going to start numbering that in the place that gives our substituents the lowest numbers. So let's try 2 ways. Let's start here, 1, because it doesn't really make sense to start out here. Do you agree? It doesn't make sense to start way over there. So we're not going to do that. So we have 1 here, 2 here, 3 here. That's one option. Then let's look at the other. 1, 2, 3. Or the orange way, we have 1 ethyl, 1 ene, 3 bromo, 3 ethyl. 1, 1, 3, 3. How about the other way? We have a bromo on 1, an ethyl on 1, an ene on 2, and the ethyl on 3. I'm messing something up. Hey Sabrina, so when you're numbering these things, oh my gosh, I thought you were Siri. So when you're numbering these things, you give the lowest number to where the parent functional group is. You put the parent functional group on the lowest number, right?
Yes.
Cool.
1, 2. That's the same thing I asked you last night.
Yeah, I think it's like some different context there. It's weird because, yeah, if you break the ties the traditional way, you would go
Yes, so you would focus
1,
on
2,
what's on your
3.
parents, so your double bond.
Okay, cool.
And so if you went in the clockwise direction, then your double bond would be starting at 1. But if you went starting from the carbon that has the bromine, then your double bond will be on 2.
Right.
So you would change the parent first and put the double bond on 1, and then you'll pay attention to the substituents later.
Cool. So yes, what we're going to do here, we're going to give our parent the lower number. We're going to start numbering from there. 1, 2, 3. Sorry about the confusion on that. So that is going to be our number. So what's our parent name here? Is it an alkane? It's going to be an alkene, right? Because we have that double bond. Cyclohexane. Ene. Yes, cyclohexene. Yep, cyclohexene. And that's our parent. Let's look at the subs on our parent. So we have a couple ethyl groups we need to talk about. So on 1, there's an ethyl, and on 3, there's an ethyl, right? So what are we going to do to say there's 2 of them? Diethyl. Now, what's the last substitution we need to take care of? 3-bromo. Are we ready to name this? What's one thing we haven't talked about yet? Stereochemistry. Double check that you do the stereochemistry. So right here, they give us a chiral carbon with its stereochemistry. When they do that, anytime you have dashes and wedges, that's a really big hint. You need to do stereochemistry there. So let's go ahead and do that. We'll do it kind of quickly. We've done this a few times. So bromine's going to be 1 for sure. Now we're deciding between 3 carbons. So we look at what they're connected to. The top one is connected to a carbon, and it's in a double bond. So it's actually, we consider that to be connected to carbon twice. So that's going to be carbon-carbon, and it's also connected to this hidden hydrogen, just 1 hydrogen. So CCH on that one. What's this bottom one? We have, it's connected to a carbon and 2 hydrogens. CHH. This right here, the ethyl, that's connected to what? A carbon and 2 hydrogens. We're going to have to break that tie. For now, we do have 1 winner, right? So this top one, CCH, beats the other 2. So that's going to be our second place, automatically. Let's go ahead and erase that so I have room. That's going to be our second place, right there. Now we're just vying for 3rd and 4th. So we can break the tie. So let's look at the bottom one first, the bottom left first. And let's look at the next carbon over. We're going to have to go 1 more carbon over. What is that? It's connected to a carbon and 2 hydrogens. This ethyl down here, if you go to the next carbon over, what's that connected to? 3 hydrogens, just like that. So now we've broken the tie. The one on the left beats the one on the right, beats that ethyl. So this guy won the 3rd place tie. This is 4th place. What do we notice about our 4th priority group? It's on a wedge. Are we going to need to change our answer later? Nope. Sweet. So we don't need to change our answer. What do we do next? Draw your arrow. Yep, from 1 to 2 to 3. Clockwise or counterclockwise? Counterclockwise. R or S? S. Do we change our answer? No. Yep, so we have S stereochemistry. Are we ready to name this thing? We sure are now. So, put in S because stereochemistry goes first.